So the topic for today is collisions. So what is a collision? A collision occurs when two or more objects interact with each other through forces. It's much like a car crash. The objects may actually hit each other during the collision or they may not. Remember, all forces require objects to be touching or to act on them. During a collision, momentum is transferred from one object to another. So according to the law of momentum, the total momentum before and after collision must be equal to each other. So the momentum of the 8 ball after the collision is equal to, less than, or more than the momentum of the cue ball before the collision. So it should be equal to. Okay. There are two general types of collisions in physics: elastic and inelastic. In elastic collisions, the objects bounce off each other with no loss in total kinetic energy and no change in shape. Perfectly elastic collisions are not common in everyday world. Usually collisions, you'll see two cars get stuck to each other. But these are elastic, they'll bounce off. So for example, in the first picture, the blue box hits the green box that is at rest, and so that it transfers that energy over to the green box, which is now moving, and the blue box is now at rest. The middle picture here with the yellow and pink ball is kind of like when you play pool. You have two balls going towards each other, and then they bounce off each other and they go in opposite directions. On the bottom picture, both objects are moving, and they collide and they still continue moving on afterwards. And now in inelastic collisions, objects change shape or stick together. In some kinetic energy is converted into other forms, such as heat, deformation, or even friction. So for example, in the picture before collision and then after collision, they both get stuck to each other. And so this is how they're different from elastic. Elastic, they would have bounced off each other. So momentum is conserved in both elastic and inelastic collisions, even when kinetic energy is not conserved or lost to heat or friction. So being able to solve for collisions is very interesting. So using the conservation of momentum, you can determine the speed and direction of objects before collision, even if we only know the speed and velocities after the collision. So accident investigators often use this approach to determine if anybody was speeding before an automobile accident. So direction with collisions is important. Okay, when we say positives, we either say up or to the right, and negative is to the left or down. So the momentum of the system before equals the total momentum of the system after. So remember, momentum is conserved. And so remember, momentum is P equals mv, and we have two objects now because in collisions we have two objects. So here's the momentum of object 1 and momentum of object 2. Initially, so this is the initial, you can't really see it, it's capital I, and after the collision, the momentum after the collision. So we can say it like this: P plus P equals P plus P, because that's the momentum. Momentum of the two objects before equals the two momentums after. Or the initial momentum equals the final momentum. Or mv plus mv equals mv plus mv. Or we can get even more detailed and say mv1 initial, mv2 initial equals m1 final plus m2 final. So let's work on some practice here. Two 0.165 kilogram billiard balls, so those are two masses for both objects, in the same direction, roll in the same direction and collide. Initially, the 10 ball has a velocity of 0.5. The 5 ball has an initial velocity of 0.7 meters per second. After the collision, the 5 ball has a velocity of 0.4. What is the velocity of the 10 ball after the collision? And so we kind of set up our information before and after. So before, we have the 10 ball. They all have the same mass, so this is the easy part. And we're given the velocities before collision, and we're only given the velocity after for the 5 ball. We're trying to figure out the 10 ball. And so it's good if you do something like this so that we have everything set up together. So this is an elastic collision because they do not get stuck together. They once this one bumps into the 5 ball, the 5 ball still moves, the 10 ball still moves. They're still moving afterwards. So we just plug in. Now that we have our chart set up, we can just plug in. So M1 1.65, V1 0.5. That's this right here, right there. I can color code for you. The next one is 0.165, 0.7. That's the 5 ball. If you like to color code, that might be good. If you're the type of person that can do that, then go ahead. Point, and then afterwards, the 10 ball, we don't know the velocity, so that's why we have a v there. The 5 ball, we do know the velocity is 0.4 afterwards, and it still has the same mass. Mass doesn't change. And so once we do the math here on the left with the red and blue, we see that that equals 0.198 and equals 0.165 v plus 0.066. So we're trying to get rid of this number, 0.066, so we subtract it from both sides. And we would subtract it from both sides. 0.066, that crosses out, and we have this over here. When we subtract these two, we get 0.132, and we divided both sides by 0.165 to get rid of the v, or to get rid of the number and leave v by itself. And so we have 0.132 divided by 0.165 equals v. So v equals 0.8 meters per second after collision. So 2.165 kilogram billiard balls roll in the same direction and collide. Initially, the 10 ball has a velocity of 0.7 meters per second, and the 5 ball has an initial velocity of 0.4. And so we set that up in our before box. After the collision, the 5 ball has a velocity of 0.2. What is the velocity of the 10 ball after the collision? So this is almost the exact same problem. We just changed the numbers up a bit. So if you want to try it on your own first, and then see how we solve it in the next slide. So we see that these billiard balls do not get stuck to each other, so we know that this is an elastic collision. Okay, and I'm gonna color code again. So this is our before. So M1 0.165 times velocity is 0.7 plus the 5 ball is 0.165 times velocity is 0.4 equals my object 1 final, which is 0.165. I don't know the velocity, so I put v plus, and then finally the 5 ball, we do have all the info, is 0.165 times its velocity, which is 0.2. Okay, and then we just do the math here. We add these two on the left, the red and blue, and when we do that, we get 0.1815 equals 0.165 v plus 0.033. Now, I want the variable v by itself, so I have to get rid of that 0.033, so I have to do the opposite to both sides. I get rid of this, minus 0.033, so we get 0.165 v is equal to 0.1485. And now I want v by itself, so they're multiplied right now. I divide by that number on both sides, so that gets rid of that, and I divide this by 0.165, and I get v is equal to 0.9 meters per second. So that is my final velocity for the 10 ball. So we see that we got that correct. A 560 kilogram moose stands in the middle of the railroad tracks, frozen by the lights of an oncoming 13,300 kilogram locomotive that is traveling 42 meters per second. So this is all before. The moose mass is 560, velocity 0 here on the left, and the train is info here before. The engineer sees a moose but is unable to stop the train in time, and the moose rides down the track sitting on the cow catcher. A lot of my students had questions about what a cow catcher is. You know, a train has this this edge that's sharp. This is a cow catcher. So the poor moose was stuck. It was stuck right there on the cow catcher. So what is the new combined velocity of the locomotive and the moose? So if you look here, after we combine the masses, because they got stuck together, and they rode together, so if they're stuck together, they all have one single velocity. So this is an inelastic collision because they got stuck together. And so the formula, this changes a little bit. The left remains the same, so we still have M1 V1 plus M2 v2 equals, but now we add the masses m1 plus m2 and multiply that by a single velocity. And so this is on the left, this is the moose, and then the train equals the combined mass of the moose and the train, v. Okay, so to get rid of that, to get v by itself, I divide both sides by 13,860, and we get our combined velocity of 40.303 meters per second. A 420 kilogram moose stands in the middle of the railroad tracks, frozen by the lights of an oncoming 12,000 kilogram locomotive that is traveling at 30 meters per second. The engineer sees the moose but is unable to stop the train in time, and the moose rides down the track sitting on the catcher. What is the new combined velocity of the locomotive and the moose? So this is very similar, so go ahead and try it on your own. Try to write your before and after chart, and also try to set up your equation. Okay, so this is your before and after chart. Just like we did before, we have a combined velocity because they got stuck together. So this is an inelastic collision. And so we have m1, v1. So this will cancel out because anything times 0 is 0. And then we have m2, v2 equals the mass of the moose plus the mass of the train because they got stuck together times v. And so to get v by itself, I divide both sides by 12,420, and our final velocity is 28.99 meters per second. All right, let's look at this problem. If you're doing your notes, we're skipping 5 and 6. If this on your notes, we'll be going over that later. It's a different type of problem. So let's go to 7. A 0.4 kilogram red block is moving to the right at 0.6 meters per second on a frictionless surface. And so we see this in the red block here. And so we put our information. M is 0.4, V is 0.6, and it's going to the right, so it remains positive here. It collides with a 0.2 kilogram block, so we put that info here for before, that is moving to the left at 0.8 meters per second. So if it's going to the left, it has to be negative. Remember, values to the left are negative. After the collision, the red block is moving left, so it has to be a negative 0.22 meters per second. Find the velocity of the green block after the collision. So notice in this type of collision that they are going towards each other and then they bounce off. And so because they bounce off, towards the end, they go opposite directions. So we know that our velocity for the green block at the end was negative at first because it was moving left, but when it bounced off, it went to the right. So we know it has to remain, we have to get a positive velocity here. So this is an elastic collision, and we just plug in our numbers just like we have before. And this is what we're looking for, that variable that we're looking for, the green block. And so once we do our math for the left side, 0.24 minus 0.16, we get 0.08. And then we have a negative here, so to get rid of this negative, we have to add 0.088 to both sides, and that's what happens here. When we do that, we get 0.168 equals 0.2v. To get v by itself here, we divide both sides by 0.2, and that's how we get our final velocity, which is 0.84 meters per second. A firecracker with a mass of 2 kilograms sits at rest on the ground. After it explodes, 1 kilogram piece flies off to the right at 50 meters per second, while the rest of the firecracker flies off to the left. What speed does the second piece have? Okay, so let's put our info first. So the cracker, the only thing we have before is a cracker. It's one object. And so it's 2 mass and 0 velocity, and then we're looking for that piece, the second piece that flies to the left. So we know our velocity is going to be negative. And we know that it's inelastic because it's explosive. So we put our info in. The reason we have 0 here is because our mass before was 2 times 0, which is 0. And we have piece 1, which was 0.1 times 50, plus piece 2, which is 0.8 v. So we do our math here. 0.1 times 50 is 60, plus 0.8 v. To get rid of the 60, we have to subtract it from both sides. That's how we get negative 60 on the left. And then to get v by itself, I have to divide both sides by 0.8. So 60 divided by 0.8 gives us our final answer, which is negative 75 meters per second, or 75 meters to the left.